Hello, welcome to everyone. It's a pleasure for me to welcome all you in this ICN2 Nano Seminar in Health and Medicine. It's a series of seminars that ICN2 is organizing in collaboration with the University of Manchester. And today we have a special guest, Professor Paolo Samorì from University of Strasbourg. But before starting with our guest, as usually, these nano seminars are starting with a presentation from a young researcher. In this case is Massimo Urban, a PhD student from Nanobioelectronics and Biosensors Group, who is going to give a kind of introductory talk, although not directly related to Professor Massimo, but very much related because what Massimo is doing and collaborators in Nanobioelectronics and Biosensors Group is related also to the use, application of nanomaterials through inkjet printing for the development of biosensors. And the role of nanomaterials in this context is very important. And what is going then to explain Professor Samorì is what indeed the potential of nanomaterials, nanotechnology to develop these kind of devices is really crucial. So now that welcome Massimo. Massimo is doing the PhD, is in the third year of the PhD, working together with Giulio Rosati, who is not here, probably is connected through internet, but yeah, Massimo, is your turn. So thank you.
Thank you, Arvin, for the introduction. Hi, everyone. My name is Massimo. I'm a PhD student at the Nanobioelectronics and Biosensors Group, led by Professor Urban Mercocci. And in our group, what we are talking about mainly is development of novel biosensing platforms for point of care, using methods which they don't require clean room, so clean room free. And what we are doing is just using, trying to use this simpler equipments that they don't require special personnel, and we combine it with nanomaterials and bioreceptors to create these platforms. The applications are different, but mainly we are focusing on two, so biomedical and environmental applications. And so let's try to have a look on what is a biosensor. So it's an analytical device that has the function of recognize a target, analyte, and having a bio recognition element that then generates with a transducer a signal that can be detected in some way. And the signal can come from different ways. So it can be optical, electrochemical, or electrical, depending on the properties and on the system that you are looking into. So these are just some examples if you want to check it out. So what I'm mainly focusing on is to develop electrochemical biosensor. And the way that I'm doing it is using inkjet printer, mainly consumer inkjet printer. Why consumer inkjet printer? Because we think is a really nice candidate for low cost point of care platform because of its simplicity. So basically this is a plug and print system. We just plug in the machine, and then the machine does everything for us. We just need to optimize the parameters in order to fit the equipment. And also because we envision a world where you have these equipments or equipment similar to this that are able to print on demand in the point of need. So everywhere in the world in a ubiquitous way, we call it. So decentralized. So I want to show you some kind of a path of my research, how it's usually conducted. And first and foremost starts with nanomaterials. So we want to fabricate, to synthesize and characterize the nanomaterials that we are going to use for inkjet printing. And especially important these properties, so size and chemical properties for us in biosensing. And size because it's a limitation due to the equipment, combined with the second properties that we are going to measure, so the rheological properties, specifically surface tension and viscosity is really important because they need to fit the window inside the equipment to be able to print these materials on surface and so on substrate. And if we have these two requirements, so size, chemical properties, and also stability, I would add, and these rheological properties, what we can do is then try to test if they are printable or not. What we do is just simply add these components inside our printers, we can change and assign the colors in this case, because this machine has multiple cartridges to do it. And we then like print this on different substrates, and we assess resolution, we assess the morphology and the properties, electrochemical, whatever like it's needed for the specific device. That they might look like something like this. So these are just two examples, but the important point here is that we are usually using temperature sensitive substrate, which sometimes require a bit of craft in the art, because of course we cannot treat these devices like normal, like putting in the oven for high temperatures, high times. So they are a bit difficult to handle sometimes. And this comes to the final step, which is actually just the application of these devices then in some real case scenario to solve real issues in the community or in the world. So I will show you some examples, and the first examples I want to show you is just the development of an inkjet printed biosensing platform using office layer equipment. So the point here was to use different kind of nanoparticles, gold and silver nanoparticles, to create a standalone electrochemical transducer. This is a 3-electrode system. It's functional. It's a device that we can use for then functionalize with bioreceptor and use it for detection of analytes. And the point of this work was to try to do it like with simple fabrication method, just using like equipment that is available in offices, let's say offices, but like really easy equipment that is not required like to have like a specific training. You can learn the way to do it. Is quite easy. And the point here was to optimize all and every single step to try to obtain like this really robust electrochemical platform for then testing in a variety of different applications that actually like I'm not exploring all of them myself, but I have really, really kind and talented colleagues that are doing it together with me and also like by their own. And the point here is that the use of these nanomaterials is really important, but also like sometimes arises to new properties and to really cool features that actually this is also my job to study. In particular, like these gold nanoparticles electrodes, as I was saying, they are printed on this temperature sensitive substrate. So it was a problem because this is a chemical procedure, like actually a procedure that's called sintering, that usually requires high temperature to make conductive films of the nanoparticles. And in this case, what we had to do is to try to find crafty ways to do it without using temperature. And this was actually the work that we found, that using a special treatment that doesn't require temperature is like done chemically. Like this is a specific treatment that is able to sinter the film as well as nanostructure in the film. So you have like this really, really porous structural electrode, which for biosensing purposes are really, really good because they increase the loading of bioreceptors that you can have, but also like generally like sensitivity and this analytical performance values. And also like what we show in this case was just, it's possible to take this and like trying to integrate it in the same printer to have like something which is possible to print and then to sinter in the same time. So actually like this integrating feeding inside the printer also is like towards this goal to have like a standalone device that produces the sensors and you can have it in your place. And then actually like also these properties, like now I will show you another example. We're trying to combine these properties of these electrodes, like for example, porous electrodes. So this nanomaterial with other nanomaterials to try to combine to have like a synergistic effect. And this actually is done for something that we are starting investigating right now in the group. And it's called like reactive inkjet printing. So the concept here is that you have like in your printer this specific model, but most of them, they have different cartridges with different colors. And what you can do is to just like mix these colors like in different proportions to create chemically some substances on the surface, which actually combining this with porous electrode, you can give rise to new kind of composites. And so what we do is like to start with one really study and well-known example, which is Prussian blue. Prussian blue, it's a derivative of ferrous cyanide. It's a complex that basically is a metal organic framework that for biosensing is extremely interesting because it has peroxide mimicking properties. So basically it mimics the action of some natural enzymes for the ones who know, are familiar with this HRP example. And basically what they do is just like breaking hydrogen peroxide into reducing hydrogen peroxide into water, or like actually like OH minus. And this is important because most of the enzymes, or some of them, they have as a byproduct hydrogen peroxide. So we can use this as a way to detect hydrogen peroxide. And so like all the world of enzymatic sensors. And what we were doing here was just like trying to study, and we started studying what happens on the surface and the mechanism how it works. And actually what we did was just like trying to print and just to try different combination of concentration and precursors and oxidant to try to understand what is the effect on a surface, but also what is the effect on the porous structure of these electrodes is possible to combine. And we saw some really interesting effects, as well as trying to monitor the electrocatalytic activity towards hydrogen peroxide. And here you can show just some examples that you can see the typical peaks of Prussian blue in cyclic voltammetry, and also like the response to hydrogen peroxide. So this was just an example to show you like also ways to combine and to use these printers like in a non-conventional way, trying to make something like which is a bit out of the box. And with this, I want just to thank you all for your kind attention. And if you have any questions, I'm pleased to answer. Thank you.
Thank you very much. Thank you very much, Massimo. If you want to do a very quick question to Massimo, then if not, we can continue. Is there any question for Massimo? Yeah, Salvo, please.
You do all of the printing on room temperature substance. Because otherwise they can't hear you at home. Sorry. Okay. So just to repeat, I suppose that you do every printing on room temperature substrate. Is it possible just to modify it to do on just preheated substrate in order to have
yeah, this is typical of the research gate printers, that they have like a kind of a tray that you can put your substrate and you can heat it in order to have like higher temperatures. What we are doing in the group, we are also trying to implement, for example, heaters inside these printers, try to do some like specific like 3D printer mixed with other printed blocks to have some heaters so we can heat at the same time as print. Because of course here the motion is like kind of is not still the paper. We are doing it, so we are studying also this is possible. Of course the temperature range would be like kind of low, but yes, it does, you can do it.
Okay, thank you very much, Massimo. Now it's a big pleasure to introduce our guest, Professor Paolo Samorì, distinguished professor at the University of Strasbourg, director of the Institute of Science and Engineering, the Supramolecular, and director of the Nanochemistry Laboratory. He is a member of Académie des Technologies, foreign member of the Royal Flemish Academy of Belgium for Science and Arts, fellow of the Royal Society of Chemistry, fellow of the European Academy of Sciences, EUROSAC, member of the Academia Europea, member of the European Academy of Sciences and Arts, fellow of International Engineering and Technology Institute, socio corrispondente, sezione di Scienze Matematiche, Fisiche e Naturali, Accademia Nazionale di Scienze, Lettere e Arti di Modena, fellow of the Material Research Society, fellow of the University of Strasbourg Institute for Advanced Studies, senior member of the Institut Universitaire de France. He has obtained Laura, master degree in industrial chemistry at the University of Bologna in 1995. In 2000, he has received a PhD in chemistry from Humboldt University in Berlin, working with Professor Abe. Before joining ISIS, he has been permanent research scientist at Istituto per la Sintesi Organica e la Fotoreattività of the Consiglio Nazionale della Ricerca di Bologna. He has published more than 430 papers on nanochemistry, supramolecular sciences, materials chemistry, and scanning probe microscopies, with a specific focus on graphene and other 2D materials, as well as functional, organic, polymeric, and hybrid nanomaterials for application in optoelectronics, energy, and sensing. Professor Samorì has been awarded numerous prestigious prizes, including EMRS Graduate Student Award, MRS Graduate Student Award in 2000, in 98, the UPAC Prize, Vincenzo Cagliotti Award in 2006, Niccolò Copernico Award in 2009, Guy Urison Prize, ERC Starting Grant in 2010, CNRS Silver Medal in 2012, Catalan Sabatier Prize in 2017. IRC surface and interfaces in 2018, Blaise Pascal Medal in Material Science, Pierre Sueur Prize, ERC Advanced Grant in 2019, the Étoile de l'Europe Prize, ERC Proof of Concept, RSS CSF Joint Lectureship in Chemical Sciences, and Prize André Coyet in 2021. He is also Associate Editor of ACS Nano, member of the advisory board of many other prestigious journals, including Journal of Material Chemistry, ACS Nano, BMS Materials, Springer Nature, and more. So again, thank you very much, Paolo, for coming here. And we are waiting now to hear your talk, the presentation about the fantastic work you are doing in Strasbourg. Thank you very much.
Well, thank you very much, Arben, first of all, for the invitation. It's a great pleasure to be here back into Barcelona, and also for the kind introduction that there was no need to go through all the list of things, which actually just, let's say, give evidence that my postdoc and my students, they were very good. So they've been doing a fantastic job, and I think I'm just a clown going around and presenting what they are doing in the lab. And so what I'm going to do today is to show you a bit of our activity on how you can play with 2D materials and combine 2D materials with molecules. And this I will use for fabricating multi-responsive electronics, but actually we see that all the approaches will be, I will give you some light about how to use this approach for sensing. Can be chemical sensing or can be physical sensing. It's written input signal out of the range. It's okay. Here it is written. Okay, whatever. I continue. All right. So, anyways, yeah, and there is a broadest the broadest family of 2D materials give access to a number of different type of systems with a different chemical composition and different structures. Actually, there are some characteristics that are shared among 2D materials that are indeed atomic thickness, the flat surface, the large surface to volume ratio, the high diversity of the atomic composition, the outstanding physical and chemical properties, and in particular the properties that are susceptible to the environment. This makes them particularly interesting when the interfacing with the environment is controlled in order to fabricate a device for chemical and physical sensing. People claim, theoreticians claim, that one can exfoliate as many as 3,000 different type of 2D materials. Now, from the experimental point of view, only about 100 has been proven, but I think there is room for expansion. Now, the diversity of the properties are such that you can have 2D materials going from the more insulating example of the boron nitride with the band gap that is higher than 5 eV, and all the way down to the superconductor that is niobium diselenide. In between, you have a number of different type of systems, different properties, can be semiconductor, half metal, semi-metal, and so on and so forth. With a variety of band gap. Now, of course, this variety of the band gap and variety of different type of electronic characteristics is such that the interaction between the 2D materials and light can be quite diverse. But this is not going to be much of the subject of today. The vision is always the one of trying to exploit the outstanding mechanical, electrical, optical properties of 2D materials to fabricate, toward the emergence of disruptive technologies. Can be in different fields, can be in electronics, can be in automotive, can be in sensing, can be in different directions. Of course, there is a lot of hopes and a lot of hype, and the demonstration still to a great extent has to come. Anyway, what I'm going to do today, I will start discussing about two-dimensional semiconductors. So we will not focus much on graphene, but we'll focus more on systems that have a finite band gap, and to use this for the electronics for sensing. And actually, before we started to play with this kind of system, we decided to try to nail down which could be the type of, let's say, challenges one has to face. And the challenge that I will tackle during my presentation today are the ones that are here in green. And then there are some other that I have no time to go through. So in particular, we will try to broaden the availability of the semiconductor and to cope with the problem that there is a scarcity of P-type semiconductor. We will play a lot with defect healing, defect engineering and defect healing in order to control charge transport and functionalization to do a control doping and also to boost different basic properties that you need in electronic devices, so charge transport and charge injection. So this is a bit the today menu. As I said, there are other challenges that have to be tackled, and these are only, let's say, the most important one, but there can be also some others. Now, our approach to broadening the to P-type semiconductor was a work that we published recently, done by Antonio Ricciardulli. Antonio, he did this, he was coming from the University of Salerno. He did his PhD in Mainz in the Max Planck Institute, and where he learned how to exfoliate different types of the materials in different manner, from the more electrochemical approach to more, let's say, sonication approach. And so what he proposed me to work on was actually on the development of new 2D materials, in particular violet phosphorus, that was predicted theoretically to have a direct band gap and to have a very high Hall mobilities. The peculiarity, of course, people have heard a lot about black phosphorus as let's say, semiconductor with high mobility, but people also know the black phosphorus has a major problem, that is the stability in air. And actually, what happened to this violet phosphorus, in a nutshell, violet phosphorus is more stable, much more stable in air than the violet phosphorus. And actually, this stability is used also to make sure that in the synthesis of the violet phosphorus, the fact that one place with the, let's say, the higher stability in temperature of the VP compared to BP, one uses a temperature during the CVT such that decompose any kind of, let's say, black phosphorus byproduct. And therefore, the red phosphorus has been used as a source of phosphorus, and as transferring agent, tin iodine has been exploited in order to fabricate this kind of crystal, which has been exfoliated by sonication DMF to get this kind of, let's say, two-dimensional object that has a size nearly of some flakes that have a size of about 800 nanometer, and actually they have a thickness of a few nanometer, namely the idea is to have 5 to 10, let's say, flakes that are pile up, stacked. Now, what we have been developing, this kind of isolated flakes, we fabricate first of all a field effect transistor using the ionic gel, so to use the volumetric gating, and we detect the mobility. There was about 2, which is not too bad. And then by combining, essentially, we fabricate an inverter in which we use as N-type, a molybdenum disulfide, and the violet phosphorus as P-type. And this actually led us to voltage gain in our device about 17. That is among the, let's say, those that have been reported for state-of-the-art or hafnium oxide. That is, let's say, the reference type of devices for this kind of inverter. Now, this is just an example of how you can broaden your 2D materials, but now I will pass to the main, let's say, core of my presentation, which actually wants to address the problem that 2D materials have a weakness, and their weakness is the limited properties tunability. And actually, here is where molecular science comes into play, where we use molecules in order to tune and improve the physical properties of the 2D materials, and also to impart new properties to the materials to make them multifunctional and multi-responsive. Now, the interaction between molecules and 2D materials can be quite diverse, from the most weak one that are the van der Waals interaction to the most strong one that are the covalent functionalization. And in between, you have a number of other type of interaction with different magnitude that can be dipolar interaction, charge transfer, or defect healing. The part on the left are those that are targeted at creating continuous films of molecules on the 2D materials, whereas the one on the right is more targeted and generating, let's say, anchoring isolated molecules. Now, this kind of interaction means that for whatever type of force you use, that can be, let's say, the more weak physisorption or the more strong chemisorption, you need to design a molecule such that has, let's say, an anchoring group that is here indicated in blue, such that will interact at the physical or chemical level with the 2D material. And then the molecule will have this red dot that is a new function that is imparted to the 2D materials. Then if you do this kind of, this is a case of functionalization with the monodentate molecules, therefore with one, let's say, anchoring group here in blue. And in this way, let's say you can create this kind of airy disks, and this airy disk that can be, the functionalization can be done in solution. And then you can self-assemble this airy disk, creating some foams. The foams, indeed, again, based on the type of red dot that you have chosen, so the properties that have been added by design, you can use for different type of application, can be wearable electronics, can be multi-responsive coating, sensing, and so on and so forth. You can also play with the bidentate molecules. Bidentate molecules means that you have two anchoring group here in green, and therefore, in this way, you can anchor, you can tether adjacent nanosheets and create networks. And so in this way, you still have the red dot that is embedded in the molecular that has been designed, and so you can create, you can add this new function that again can be used based on the dot you chose. You can be used for energy storage, for example, like supercaps or batteries can be used for tuning the electronic properties. You can use it for catalysis, you can use for desalination, you can use it for sensing. It really depends on the design of the molecule that you chose. Now, what I will do now, I will actually go step by step, give you some example of how molecule can be used to improve fundamental processes in electronics based on 2D materials, particularly using as a representative, let's say, a prototypical type of device, the field effect transistor, which is of course let's say the element in the 2D electronics, and actually that is characterized by different type of processes. Can be charge injection between the metallic electrode and or charge extraction between the metallic electrode and the 2D materials, the charge transport through the 2D materials, and the gate modulation, that is what you have at the interface between the dielectric substrate and the 2D materials. So we will actually start with the charge transport. And this kind of chapter of my presentation start with the consideration then, well, here I talk about transitional metal like co-organized, but anyway, any kind of 2D materials are defective rich. Okay, so you have to cope with defects. And so actually it's better that at this point you just use and turn it to your advantages, because anyway, defects are there. And so that is something, for example, we have reported with Simone Bertolazzi in about 5-6 years ago. So Simone came after a PhD thesis done at TPFL with Andras Kiss, where he had been doing a lot of devices based on MOS2. And so what we decided to do, I mean, molybdenum disulfide in the best case scenario can be the Scotch tape one, flakes, the monolayer, every 10 by 10 nanometer, you have a sulfur vacancy. Okay, so the idea was to try to make use of it, because sulfur vacancies anyway, and in any ways, defects are reactive sites. But actually, it might be that one defect every 10 by 10 nanometer is not enough for you. You want to have more, because you like to have more, let's say, reactive site. And so what we have been doing in this study has been using the argon beam of the XPS in order to generate defects, so to extract atom of sulfur to create more and more sulfur vacancy. Of course, this means that from the electronic point of view, the materials get poorer and poorer. You can see here that increasing the number of sulfur vacancy, the mobility exponentially decreases, the electromobility. But of course, because sulfur vacancies are scattering center for the charge transport. But actually, what it is known that sulfur vacancies can be also yielded by thiolated molecule. So here we just took a very basic thiolated molecule with entire commercially available, and we use this in order to heal these vacancies. And you can see that this is the initial IV characteristic. This is the one that you have after the ion bombardment, and then we recuperated to a great extent upon butanediol treatment, the initial IV characteristic. So overall, we not only have been healing sulfur vacancy, but we also can use this to graft molecular function to the MOS2 when instead of using butanediol, the molecule is a bit more sophisticated, so integrates a functional unit. And now, just to give you an idea, this is a paper that has been submitted recently, so it didn't appear. The sensitivity of this kind of, let's say, interaction and, let's say, perturbation of the electronic state of the MOS2 is such that we have been using in this study to discriminate isomers. So as you know, isomers are very complicated species to be discriminated from the chemistry point of view, because these are molecules that have the same mass. And so the idea here was to do a very basic study to take a thiolated molecule, with a trivalent benzene with 2 fluorine atoms that can either pointing down or pointing up. And actually, this means that the dipole of the molecule can be the direction of the dipole of the molecule, the orientation of the dipole of the molecule can be controlled in such a way that when we use the 226, the double fluorine benzene thiol, we have a dipole that is pointing out of the surface, whereas when we use the 3,5, we have the dipole that is pointing towards the surface. In such a way that the first one, the 2,6, induce an end-doping effect, and the 3,5 induce a p-doping effect. That can be read in a different manner. It can be read by Raman, it can be read electrically. So this is just to give you an idea of the sensitivity of this kind of approach that eventually can be used also for sensing different type of small molecule. Of course, here is key to bring the dipole as close as possible to the surface. Now, then this is what can be done with monodentate molecule. Then what happened about in 2017 when we published the first paper with Bertolazzi, I was in Dresden. After the working hour, I met Jonathan Coleman. So Jonathan Coleman is a pioneer of the liquid phase exfoliation of 2D materials. So in 2009, he published the first paper about graphene, and then he has been exfoliating with different type of liquid approaches, all the possible type of 2D materials. And then we were discussing in front of a beer. At that time, Johnny just published this paper in Science, in which he claimed that he has made all printed thin-film transistor network based on liquid phase exfoliated nanosheet. Now, here there was a number of things that I was unhappy with in this paper. First, he used the term network, which we still disagree, because I will tell you in a second why for me network is not what he published. And second, what I was unhappy is the fact that he makes this molybdenum disulfide devices, transistor with mobility were, let's say, pretty low, 10 to the minus 2, 10 to the minus 3 centimeters square per volt per second. So I told him this kind of mobility you can reach with organics in a much better manner. And then he tried to convince me that actually it's just the beginning of a story, the way he says it. But, and also he told me that the problem that the reason why he got so low mobility in the device is because there was a big problem in terms of interflakes electronic connectivity. Essentially, he has been printed a number of flakes in between the source and drain electrodes of a transistor, and the charges are not able to jump from one to the next nanosheets. And so the idea is that I told him we have to find a way how to create percolation pathways for charge transport to force the charge to go from one sheet to the next one. This is something that in the field of, let's say, organic-based electronics has been done, for example, by combining polymers with small molecular crystals. Now, so at that time, Stefano Ippolito started his PhD, and I gave this as a project of his PhD. And the idea, let's say, in a cartoon is the following, that if you have this kind of 2D sheet and you deposit this on a basal plane of a surface, it's like small flakes that are completely disconnected. And so the concept is to use the complementary piece of the puzzle in such a way to bind the adjacent nanosheets. Okay. Now, in more chemical way, let's say way of expressing this, it means that we have this solution process disulfide that actually we've proven this work to be to work with molybdenum disulfide, rhenium disulfide, and tungsten disulfide, and then we combine this with let's say a conjugated molecule which has two anchoring group that are two thiol group in the para position of a phenyl ring. And this way we can actually covalently interconnect the network, create covalently interconnected network, which means we have two effects on the same time. First, we yield the sulfur vacancies that are on the basal plane of and at the edges of the MOS2 or the other disulfide, and we covalently bridge the adjacent nanosheets. Okay, so that is the concept. Now, how we fabricate the device is pretty simple. We took a commercial, let's say, substrate of silicon dioxide from Fraunhofer, which exposed some pre-patterned gold electrodes. The ink coming from Johnny Coleman, we drop casted our ink in between the two electrodes, and then we obtained the one that I call films. So here is where me and Johnny still disagree. I call films where the flakes are disconnected. And then actually we put this in a control atmosphere. And we did this and then we drop cast let's say, a solution in hexane of our benzene dithiol. We chose hexane because they exhibit a minimal doping effect on the MOS2. And then we did this in a controlled atmosphere to avoid photooxidation, and actually in the dark as well. And this is what I call network. So this is network, and those up here are the films. Now, so the network is what we have on the left with the sulfur vacancy or defects, which have been, let's say, used as anchoring site to create the network of these nanosheets. Now, how we can prove that this kind of network has been formed? We can look at the Ramans, at the XPS spectra. The XPS spectra, we look at this kind of substoichiometric component in the film, and the intensity of this substoichiometric component reduced from 5 to 0.5% upon network formation, demonstrating that we have a decrease into the defectiveness within the film. Likewise, we perform also Raman spectroscopy. This was done by Andrea Ferrari in Cambridge. And actually, we focus on the full without maximum of the E12G peak and the A1G peak. And we saw that upon tile exposure, it narrows down. And there is also a blue shift, an increase of the ratio between the two. This, again, is an indication of the decrease of the defectiveness within the film. In particular, what we found with Raman, that most of the defects are at the edges and not really on the basal plane. Now, upon network formation, the film became a network that exhibit a much higher hydrophobicity compared to the film, which allows to have, let's say, networks that are stable in water, don't detach from water, whereas the film was detaching once was exposed to water. Therefore, of course, for let's say, for water-based application, the network is more interesting. And then we were interested to see we can improve the electrical characteristic of the device. And we use again the liquid-gated TFT, because having the dielectric liquid that penetrates to the free volume, we have a volumetric gating effect. And to make the long story short, upon network formation, we have an increase in the field effect mobility of 10-fold, an increase of the ion-IF ratio in the transistor of 10-fold, no change of the threshold voltage. Therefore, we have an absence of doping. We also have the device switches much faster, of 1 order of magnitude faster. Now, what's next with this approach? I mean, this is nothing else than starting from 2D flakes and bottom up creating networks, and which can be used not only for electronic application, but can be used also for sensing application. So the next is explore this approach, different type of 2D materials, and essentially use different type of bridges that can be a bit more functional. And for example, very recently, we have been working on this project in which we use the MOS2, and we wanted to create network with a doubly thiolated but receptor for chemical sensing. And so actually the receptor is quite banal, and also the analyte is quite banal. We use the terpyridine, and actually we use this for cobalt ion sensing. And we utilize the, let's say, electrical readout. In particular, you can imagine that upon treatment of the flakes of the MOS2 with this kind of molecule and successive complexation, you can modify both the charge transport at the intraflake level when eventually the functionalization is at within the flake, or at the interflake level, which actually you can have the transport through a receptor with or without the metal center. So I will show you just the approach, not the result, because I think it's more interesting to generalize the story. We have sulfur vacancies in the MOS2, and so we added the preform complex zinc terpyridine complex, and then actually once we have created the network, that is something like this, we have treated with a proton in order to release the zinc ion and to have an empty terpyridine cavity for hosting the new receptor. Okay, you can of course expand this also to other type of analyte. The way we have done this it was using a microfluidic chamber, because it allows us to have a much better control over the formation of this kind of 2D network. Namely, we have an inlet and an outlet, and essentially we can inlet a MOS2 or the doubly thiolated molecule, and stepwise you can see that first we put a few flakes, we play with very low concentration of MOS2, then we decorate with this W-related molecule, then we insert another, again, the MOS2, and we continue stepwise. Of course, in between each step, there is a washing with the pure solvent. We continue until actually the picture is missing the two electrodes that are on the two sides, and after each step, we measure the current passing through this kind of device until a percolation pathway is generated, and there we stop. We can start using the device for the chemical sensing. Okay, and so this approach allows us to have high coverage, a very low thickness, and have a pretty good control over the structure of this kind of device. So the microfluidic chamber is a very banal one that we fabricated with a 3D printer in our lab. Now let me pass to the charge injection and charge extraction. Now I anticipate that this is, I think, is a great project, is a great result, but I would not recommend a normal person with my hands like mine to try to do it because it would be nearly impossible. So that the idea is to develop some asymmetrically functionalized top contacts. So the idea is that typically people in any kind of in different type of transistor, people in order to modulate the charge injection extraction at the interface between metallic electrode and any kind of semiconductor, can be organic, can be inorganic, people have been treating metallic, in particular gold electrode, with molecule, for example, chemisol self-assembled monolayer, in order to increase or decrease the work function, and to have the ideal work function to have a better alignment with the semiconductor. This is what people have been doing for, let's say, bottom contact, bottom gate devices. But actually, what the people would have loved to do is to do the same game, but with top electrodes, so with top contacts. Why? Because the top contacts offers, let's say, much greater, a much larger area of injection. And so that is what I will demonstrate to you. It can be used in 2D materials, but can be used also in case you have organics, for example, as top contact. So the hero of this story is Hanbin. So Hanbin, he has an amazing brain and fantastic hands. At least the hands are much, much better than mine. And so the approach used is, on the paper, is easy, but then to reproduce, I'm not sure that many people can do it. So he took a very simple substrate, and then he took a mask like a TM grid, and he evaporated gold pads. And then, so these are the gold pads. He evaporated with a thickness of 50/10 of nanometer. And then he has been chemisorbing. This is, as a proof of concept, been chemisorbing molecule that actually they are thiolated. They can actually have a dipole. They can point towards the surface or out of the surface. So one that is to lower the work function of the gold electrode, that is 5eV, is the amino functionalized molecule, the one that is called DAPT, here in blue, or the perfluorinated version that increases of 0.7 EV, the work function of the gold. So he can actually functionalize each electrode with the molecule he wants. To prove that this, let's say, is, has an effect on the field effect transistor, what he did is, so he actually, once he has this electrode functionalized, he takes it with a micro manipulator, and he turns it upside down, and he lands this down on the surface of the semiconductor, okay? And I have a statistic of hundreds of devices, so it's something that is highly reproducible by him. And so to the point that he can also put the electrodes very close by. The closest channel he reached was 7 nanometer by hand. Okay, so I told him that he is doing the wrong job. He should go to work for Rolex and become rich instead of being a chemist. But okay, that's his problem. Anyways, here, when he used the two, let's say, equally functionalized electrodes, so the symmetrically functionalized electrode, he can optimize the charge induction, the transistor, when he uses the DAPs that lower the work function of the electrode of gold. And so he reached mobility of about 30 centimeters square per volt per second, to be compared with the pure gold that is about half of this, so about 15, and below 10 in red is when the unfavorable work function is characterized the gold electrode. So when the perfluorinated molecule is functionalized. Then actually he went a bit further. So he functionalized in a symmetric manner the source and the drain electrode. And he used this to fabricate a diode, which shows a good asymmetry that is being quantified by a rectification ratio of 10 to the power 3. So now, of course, what is impressive of this story is the fact that what we haven't yet published is can do the same game also molecules that are physisorbed. So they don't need to be chemisorbed and anchoring very strongly. You can physisorb a thick, let's say, a 20, 30 nanometer thick layer of molecule, can be electron acceptor, electron donor, and again turn them upside down and put them at a distance. So the statistic is about 20 nanometer with some extreme of the 7 nanometer. Now, I asked him if he could also, let's say, put the electron in a controlled manner of, on a single nanoribbons. He said the problem is not my hands, it's the optical microscope. Okay, that actually below 500 he cannot see. So he claimed that if the ribbon is longer than 500, he has 95% of success rate, at least his ends. Anyways, so let's pass now to the van der Waals heterostructure. And of course, the idea is to grow a second layer on the top of 2D material. This a kind of activity, say our perspective as a activity was something that we have summed up with Marco Gobbi already a couple of years ago in this progress report, and actually in which we have been, let's say, putting down our ideas that we develop later on. That is what I will show you now. The idea is the idea of an hybrid. So let's say you have an hamburger and you have a slice of cheese. You taste the hamburger as a given taste. You taste the cheese as a given taste. The sum of it, it doesn't have the sum of the two tastes. You have a new taste that actually makes it more interesting. And of course, you can create, let's say, multi-stacks, and the flavor or the properties can become more and more interesting. Now, of course, our inspiration is one of the van der Waals heterostructure that has been reported thoroughly by a number of physicists, and actually the possibility of manipulating the properties, for example, by simply rotating one of the 2D materials on top of each other and develop 2D periodic potentials. Now, that is what a physicist would do. If a chemist instead, what they would typically do is take any kind of 2D material and literally throw on the surface of these 2D materials either an electron donating or electron withdrawing molecule and have a controlled doping effect. Now, first of all, I like to stress that watch out about any kind of solvent you might use, because it's not innocent. So the solvent, these are a number of molecules that you might think to be innocent, to be, let's say, to be used to wash surface of 2D materials and not to dope the 2D materials. And these two papers that we, Ye Wang have published in our group shows that actually all these molecules, they actually act as dopant, okay? So the take-home message of this paper is if you can deposit molecule by vapor deposition, that is always much better. So avoid the use of any solvent, because even the most simple one, they are doping to a certain extent. Now, in fact, let's talk about doping. Let's look at the mechanism of doping and reversibility. Now, the first part, the first thing is there are two different mechanisms that you can dope to the materials with molecule. One is actually what you can achieve by using molecules that have a high dipole moment, and if you solve them on the basal plane to the materials, so this would be the electric field that is emanated by the dipole that would behave as a local gate, would shift the work function of the materials and induce the doping effect. And so that actually, at this point, playing with dipoles, the more dipole you have all oriented in the same direction, the better it is. So to make the long story short, if you want to boost this effect, you need to try to exploit collective effects. The second one is based on charge transfer, where is, well, I will show you this in a minute. So collectivity is that you can achieve by self-assembly, something that allows you to have a high effect of doping. And then if you play with responsive molecules, this is something that you can actually turn on and off the doping effect. So in other words, what we do is to grow a superlattice of molecules on the top of the 2D materials. So you play with LIGO, and the way to play with LIGO is very simple, because let's say both graphite, which has the same basal plane of graphene, and the MOS2, they love very simple molecule, the simplest molecule ever, that are long alkane. And so this is proven by the fact that, for example, they create a lamellar structure that has been visualized by scanning tunnel microscopy here. And so at this point, the chemistry of alkane is simple. If you want to add a new function, you can attach either at the edge of the alkane or in the center of the alkane, and you use the templating effect of this lamella formation through the kind of physisorption of the molecule on the surface. So you use this to do precise function decoration. And Well, I don't know why these blue things are not supposed to be there, but this is from PC, it's from Mac to PC. We have this gift. Anyway, what I will show you that to reach multifunctionality, now I know what it is. These are numbers, 1, 2, 3, 4, 5. To reach multifunctionality, what you can do is to do like what nature does. Nature put function at interfaces. So what you can do in a transistor, you just have to think, where are the interfaces in this transistor? And so they have an interface between this electrode and the semiconductor. You have another interface between this electrode and the other semiconductor. You have the interface between the environment and the 2D materials. You have the interface between the electric surface and the 2D materials. So these are 5, and actually you can also functionalize the 2D materials. So these are 5 places where you can put function. Function means molecule that have a specific functional group that can add a new properties to the materials or to the device. And so then our approach, the one we're using stimuli responsive system, they can respond to light, to electrochemical stimuli, or to magnetic field. And now this actually starts from the idea that a field effect transistor is typically a monofunctional device, and that it can be turned on and off by applying a voltage to the gate electrode. And so it's like having a remote control with a single button. And actually my goal is to add more and more buttons to the remote control. And so to integrate more function in a single device up to the dream that is a real remote control. And so we play with photochromic switches and play with photochromic switches. These are the 3 most famous ones. I mean, photochromic switches are small organic molecules that are able to undergo efficient and reversible isomerization between different states that have different properties. So the most famous one are azobenzene, that you can switch from the trans to the cis form with UV light. You can go back with visible light or thermally, because the state here is metastable. Or the directly you can switch from the open to the closed state with UV light and go back with visible light. What is peculiar here is the 2 states are thermodynamically stable. And the third one, that is spiropyro, you can switch from the spiro to the mero form with UV light. You can go back with visible light or thermally. Now, and here you can see that there is a major difference in the dipole moment in the spiro versus mero. Whereas the major properties that is changed in the R18 are the energy level. And here there is a bit of change of dipole moment, but there is also a big change in the conformation of the molecule. So we use photo switching molecules again to translate an incoming light input into the change of the material properties. Now, I will actually go skip this part because I think I will not be able to arrive until the end of what I want to show you. I will tell you very briefly the approach of this Marco Gobbi story that we published already 4 years ago. And the idea is to have a spiropyran with a very long alkyl chain. The R is a C18 chain. And so the C18 chain imposes the formation of a lamella structure. So we can control with atomic precision where we locate the spiro head group. And in this dry films prepared by spin coating, actually we can in situ with irradiation different wavelengths switch from the spiro to the mero and vice versa. Now this can be used if the substrate is MOS2 or graphene. You can use this to dope and undope the 2D materials. Well, I can skip the characterization. You can see how in the transistor we start in black with a clean. This is the case of graphene, the clean, let's say the clean device in black, and then in red with a small end-doping effect upon physisorption of the spiro. And upon illumination with UV light, we have it triggered isomerization from spiro to mero. We have a major end-doping effect going to the blue curve, which is totally reversible upon visible light illumination. And with a big, strong end-doping effect with a current concentration change that is pretty high. You can do the same also with MOS2 devices. The same story, no need to go into the details. But let's focus on the charge transfer approach that is based on the energy level alignment, which determines the doping, which in order to, by favoring the transfer of electrons either from the materials to the molecule or vice versa. And this, of course, we make use of the R18, that are those that in the 2 states they have different energy levels. And actually, the idea is we use the tungsten diselenide. This was a PhD thesis of XC and Q. And in the first part of my this story, we use the tungsten diselenide and a thickness such it was acting as a dominant electron transport semiconductor. Because depending on the thickness, the tungsten diselenide can be N-type or can be actually ambipolar. We use diarytin because it's high fatigue resistant, thermal stability, and phototunable energy effect. So the idea is very simple, that we take the tungsten diselenide, this conduction band is 3.5 eV, and we chose and we designed and synthesized with Stefan Hecht, our collaborator in Berlin, a dielectric such that is LUMO is in the closed state is within the band gap of the semiconductor, and the open state is out of the band gap. So what does this mean? What does it mean if you have a state of the dopant that is inside the band gap of the semiconductor? It means that this molecule, our dopant, will behave as a trap for the charges of the semiconductor. Whereas if the molecule has a level that falls out of the band gap, the interaction is pure electrostatic. So essentially we can dope and undope our material by changing the state of the dielectric. So the device was fabricated in a pretty simple manner. Exfoliate tungsten diselenide, transfer this to silicon dioxide, fabricate the gated field effect transistor with a laser writer, and by depositing gold metal contact, vacuum anneal to get rid of all the resistance, and then we've spin coated a thin layer of dielectric of about 3 to 4 nanometers. Let me get some water. And then what we did, we put this in the dark and we did electrical characterization. Electrical characterization are done either under illumination with UV light or with visible light. So we start from the bare tungsten diselenide with a given mobility. Once we deposit the dielectric in the open state where it is not trapping charges, we have a 20% decrease in the field effect mobility. And then actually at this point, what we do, we illuminate with UV light. So we close the dielectric from the open to the closed state. And you can see that we create traps such that we have a decrease in mobility of 50%. Essentially what we are doing, we are forcing the electron to go within the band gap of our semiconductor because that is in the closed form. And then at this point, we read it with visible light and we go back to the initial mobility value and the initial threshold voltage value. So we have undoped our film essentially. Now, if you play with the different thickness tungsten diselenide, they can act as ambipolar devices. And so this is what we have done. And in this study, what we have performed is we physisorted a blend of 2 different dielectric. One that is a very same that we did before, that we used before, that is used to trap and untrap electron transport. And so whose energy level are designed based on the conduction band of the tungsten diselenide. And the second one actually is another dielectric such that is HOMO level is in the closed state in the band gap of the semiconductor, and the open state is out of the band gap. And so to make the long story short, upon illumination with UV light, we can both bring into the closed state and create traps. Create traps such that we can decrease of 96% the whole mobility and 40% the electron mobility, which are totally recuperated upon illumination with visible light. Okay. So now this of course can be also supported on a flexible substrate. You can make different type of let's say bending cycle, and this kind of photoresponsiveness is retained. Now let's say the last part of this multiresponsive electronic is related to a thought. They thought that the materials is perfect because you can create a very controlled interfaces with the let's say with the top and the bottom let's say surfaces of the material. And so we can actually use a kind of Janus approach to harness multifunctionality by exposing the 2 faces to different local environment. And so that is what we have done. What I showed you so far was the using photochromic layer, which we decided now to put it underneath the 2D materials because this can be easily assessed, well, easily, let's say, it can more easy be assessed from far away if we are able to have light that is going through all this stack of stuff that we have in between, that I will tell you in a second. And so we can change the state of the photochromic layer. So we put this underneath the tungsten diselenide, whereas on the top of the tungsten diselenide, we decided to play with the ferroelectric layer. And now the ferroelectric layer, we did not reinvent anything. This is, we use a polyvinylene fluoride trifluoroethylene that has been used thoroughly in organic electronics, for example, combined with the polythiophene in order to fabricate device that respond to an electrical stimuli. And so what we have, this approach we have been using to and reporting to different type of papers. And the difference is essentially what kind of photochromic molecule we have been using. In one case, we use a chemisorb layer of spiropyran that has been functionalized with a silane unit that could chemisorb on silicon dioxide. And so the spiroide group is exposed here on the top, therefore it's facing the surface of the tungsten diselenide. Then the rest is the same, the tungsten diselenide, the ferroelectric layer, and the gold contact. And here, that is the case I will explain you more thoroughly, is we have a physics or diarylating layer that is the same that we'll be using so far. Now, I don't think I need to go too much in depth about ferroelectricity. When you apply essentially an electric field that is higher than coercive field, the dipoles start to align, okay? And so you create, you can control this kind of dipole that are at the interface with the 2D semiconductor, and therefore you can control let's say the doping of the 2D semiconductor. Yeah, let's go pretty fast through that. So now the first thing that I was honest in saying before, that I was not sure if I could pass light through all this stack, in particular because the ferroelectric layer is 600 nanometers thick. Okay, so it's a lot of, it's very thick. Anyway, this it turned out to work because we were able in this kind of stack to irradiate with different wavelengths from the top and change the state of the diarylating, such that you can see that we can change of 60% the current through the junction. Likewise, we could, in this kind of device, use the control with the electric field that is applying between the top electron and the bottom electrodes in such a way to control the alignment of the dipoles from the case where we apply plus 60 volt, where the dipole is pointing down and we have the highest current possible, to the case of minus 60 volt, that we have the dipole pointing up. And here as well, we have a change in the current about 65–70%. So this is the plot that combines the two stimuli. Essentially, we start from the diarylating in the open state, where we have, let's say, no trapping and all the dipole pointing down, so higher current. Then we irradiate with UV light, we close the diarylating, and we lower the current through the junction, still the dipole are pointing down. Then we apply a minus 60 volt, such that we swap the orientation of the dipole, the ferroelectric molecule, and we have the lowest current possible. Then we irradiate with visible light, we reopen the diarylating, then we apply 60 volt, and we go back to the initial, let's say, state with the highest current possible. Now you can actually use a fast laser, and each pulse, you have a finite number of diarylating that pass from the open to the closed state, so you create more and more traps, and you decrease the current stepwise. And so let's say this is something done in my laboratory, and we are not equipped with fast laser, so we can go only to 84 distinct level. When this experiment was done, but using organic and semiconductor in the lab in Nova Gorica by Guido Bratina, we could reach around, let's say, over 256 levels, so 8-bit memories essentially. Now you can also apply voltages that are just above the coercive field, and you can have a different type of, let's say, number of dipoles that are oriented, and you can assess here a different 9 distinct levels. So essentially, if you combine the two stimuli, 84 plus 9, you can have 756 different levels that you can assess. And actually, they are pretty robust. They both in their own states, both the diarylating that we demonstrated they can last for over 2 years, and the ferroelectric is something that was already demonstrated to be very robust. If we use a very fast laser, so 3 nanosecond laser, we can go actually from the 9-bit to 12-bit memories. So let's say our approach is the one that is about functional diversification, that is, let's say, pursuing the more than more approach, and you can use any kind of stimuli responsive system. You can also look at all this in terms of, let's say, neuromorphic devices. Okay, so that's something that we are starting to do in my laboratory, and doing different type of neuromorphic logic type of operation. Now, let me, the last 5 minutes, I would like to talk about pressure sensor, because this is something very, very cool, if I can have 5 minutes. So this project was started from, I was lucky that Solvay decided to pay us a PhD thesis that blue sky. So I could start a project in which I had zero track record. And so no one would have financed me a project like this because it was a bit too crazy, given what we have done in the past. And what we decide to do is to fabricate a pressure sensor. Pressure sensor can be fabricated with sensitivity in different regime, depending on the application you want to use. And we were interested in the low pressure regime for medical diagnosis. And my idea was pretty simple. The molecule can be seen as springs, and springs can have different conformation. In this case, spring can have different conformation when applying a force or a pressure. And if you put on the extremity of the spring, let's say some active, electroactive or property-rich kind of nano system, for example, you can have different type of electronic crosstalk. And so this was a work, it is by Sambo, done under the supervision of Arthur. And the idea was to have this kind of multi-layer structure of graphene-based system alternated by molecular springs, such that when we put on the top of this stack something very light, it would compress the spring. And now my idea is that this distance, so the length of the spring, should be tiny such that it's below 2 nanometers. So we are in a tunneling regime. Okay, so minor changes of distances can be read, can bring to a big change in the electrical readout. And so the idea was pretty simple. We took GO from graphene, and since we wanted to grow, as you can see here, edge on the molecule, we decided to do ring opening reaction. So we play with amino functionalized molecule, and now we chose 3 different types of molecules with the same contour length, more or less. One that is ethylene glycol based. The center one is alkyl based, and the one on the right is biphenyl. So in other words, we have a flexible, medium, and rigid type of molecule. And so we make this kind of airy discs. And so my idea that I did mind that I wanted to exploit the Hooke law on the nanoscale, essentially by changing the type of chemical of the composition of the backbone, I would change the force constant of my spring in such a way that when I apply a weight on the top of it, there will be the most flexible one will compress more. And compress more means what? Means that actually the disc will be more tiny, and so the tunneling current change would be higher. So this is a kind of vertical junction we fabricated, and so we essentially is a very simple type of device architecture. The way we fabricate, we took a commercial, let's say, foils of A5 of PET with ITO, and we cut small rectangles of 13 by 20 square millimeters. We spray coated on the top of the surface this kind of functionalized graphene oxide, functionally reduced graphene oxide. And then we did this on the 2 surfaces. And then we close, so 3 micrometer thick film here, 3 micrometer thick film here, we close like a sandwich, and we wire up with copper electrodes. And so essentially we have an active layer that is 6 micrometer thick. And we keep our lab with a force gauge. And essentially, this is the most important plot of this study, that we look at, upon application of pressure, how it changed the resistance divided by the R0. You can see that there is a bigger change when the molecule number 1 was used, so the most flexible one, and the smaller change when 2L3 was used, and actually the 4 is a pure GO-based device. So in other words, when you use a flexible molecule, they have a higher sensitivity. So the sensitivity scales with the persistent length of the molecule. That is a parameter used by polymer physics to quantify the rigidity of polymer chains. So the sensitivity is pretty low. It is lower than the state of the art. This was something that was referring to a paper of a few years ago, but still sensitivity was pretty high. The detection limit was pretty low. We could do many cycles, and also it was operating with very low voltages, such that Chambaud could put this device on his neck and on his wrist and measure the radial and the carotid artery pulse with a very high resolution, and he could determine these 2 peaks, P1 and P2, and people that are in the business know that the time difference and the height difference is very important to monitor the health of the patient. Now, what we learn out of this study is that essentially we combine conducting materials with some flexible materials that has a controllable, let's say, mechanical properties, in order to create this kind of device with tunable sensitivity. Now, I was also very interested in space confinement in order to have a device with different pixels with different sensitivity. And so what I decided as a new project to play with negative resist. And the idea is that we use this kind of molecule here coming from University of Mons. Actually, this upon cross linkage, it creates this kind of polymer that, and I mean, upon eating, it creates this polymer that can cross-link at increasing at higher and higher temperature. So upon curing temperature, we are increasing the degree of cross-link such that my understanding was as more you cross-link, the more you rigidify the phase. And you can see that actually the Young modulus is increasing drastically with increase of temperature of our curing. And so we can modulate the mechanical properties. We can also modulate the mechanical properties by deciding how much RGO we use and how much polymer base we use. Of course, we change the resistance, but we change also mechanical properties because RGO is the one that brings, let's say, electrical conductivity, and the polymer is insulating. And so we fabricate the very same device and pressure sensor. And so you can see that when we use more soft material, we have so more polymer, we have a higher sensitivity, and lower sensitivity is when we use more RGO. I will not go into the detail, but of course, so you can tune the sensitivity by the composition, RGO versus polymer, and by the temperature of the curing. Now, the very last thing I want to show you, which is unpublished, is the use of this for doing real health monitoring. So what happened after we published the first paper about this pressure sensor, we were contacted by some doctor in the hospital of Torino, and they were working on developing a new tool for doing diagnosis of cardiovascular diseases to be used in point-of-care devices. So the idea is pretty simple, that the point-of-care device typically used for cardiovascular disease is the blood pressure. And the blood pressure is not a diagnosis. You can measure at home, you get the value, it tells you how you feel now, but in a week, you can have an heart attack, okay? It doesn't predict anything. Instead, they are working on this kind of, let's say, measurement that is called pulse wave velocity. Pulse wave velocity is very simple, that you measure the speed of the blood, the signal that goes from the femoral into the carotid, so at more or less 1 meter distance. If you have any clog, the rate of this signal will be much slower, okay? And this is predicted because clog, so the fact that the blood cannot go through the arteria is one of the main sources of cardiovascular problems. And so the idea is that we put our device, one at the femoral and one at the carotid. There was actually a group in the Polytechnic of Torino that has developed the whole software and device such that we could, let's say, interpret the data. Here you can see this person in the hospital of Torino. The major challenge here was actually to find something that could really fit and adhere on the body, because let's say the body of a 50-year-old man with a bit of belly and a female of 20 years old super thin are completely different. And so that is really was a major challenge in this study. That still we found a solution, but I'm not sure that can be really generalized. And so while this is the monitoring of this signal, and then the time differences that is used to quantify the sensitivity of our device. Nowadays, this kind of measurement are done with these two tools that cost 20,000 euro, have to be done only in hospital by doctor. And whereas our approach can be point of care, can be powered by a supercapacitor, and it has the same performance of these two tools here. Now, of course, I don't want to sell it now as a new technology. There is a lot of things to do there, but I think there is a very high potential. With this, I'd like to thank all my sponsors, in particular Europe, through my ERC grant, through different types of Marie Curie, the graphene flagship, and the people that really did the job. So my lab is let's say, is crowded by a lot of chemists with C. There are some physicists, some engineers, because if you want to play with molecule, chemists are much more skilled. But if you want to fabricate working device, engineers and physicists are much more able than chemists. And with this, I'd like to thank all of you for your attention.
Okay, thank you very much. Thank you very much for this very, very interesting talk. So we have time now for questions. So who is willing to ask Paolo? I may start while you are thinking. So very, very interesting, Paolo. So what you are doing, amazing research. I have a very general question about all these materials. So graphene, molybdenum sulfide, tungsten sulfide you are using. So for either the field effect transistor or other electrical devices for pressure measurement. So what is the main difference that one, for example, can check and select either one material or the other? For example, in case of the first applications you show about field effect transistors, so what is the main difference looking between the different materials?
Well, first of all, okay, for FET, I think one can forget the graphene based. And so at that point, and that actually, if you look in the community, probably 80% are still on the graphene base. So you get rid of 80%. You remain with 20%, and probably about this 20% that is left, I would say that 10 are on MOS2. And so I think there is really a need to expand to new materials, okay, to have access to new materials, but also of a good quality. And that is not obvious, okay? So I understand now this new call of the AC that is insisting of the next generation to the materials because there is really a need to broaden, because if the theoreticians are correct, this 3,000, I don't want to reach the 3,000, but I think we can go further because there are a lot that come from nature and they can be very cheap, okay? So of course the cost is an issue. You want to make a technology. If you start from the graphene to the MOS2, the cost increase quite drastically, okay? Then it's a matter if you're processing, if the processing is what cost you, or the materials what cost you in your business plan, okay? So for us, we are not materials maker. We can exfoliate to the materials, but I think probably there is people that can do better than us. But what we try to do, I think we don't have big hopes from the 2D material side. I think we try to add to cope with all the problem of the 2D materials by adding molecules, okay? That is what we can offer, I think. And so that's a bit the way we play with it. I think people will go further with, I mean, thanks to the selenide, there has been a lot of effort spent on that materials the last 2 years. I think this will vanish soon, you know. But people are like this violet phosphorus, we came out with it. Now there are a bunch of paper coming out. People are quite slow in coming up with new materials. I don't know why, probably because science has need this speed to.
Also, stability issues, chemical stability.
Chemical stability is key. So that's the reason why black phosphorus probably is to be forgotten, but the violet phosphorus doesn't have this problem. Okay. So the devices are in air and we keep there for months and without any problem.
And I have another question about the last, so this pressure sensor is really very, very interesting. So I was wondering that one can do also the same with molybdenum sulfide.
Yeah, for sure.
These,
yeah, but in fact also.
What is the differences maybe?
Yeah, no, totally. I mean, I don't want to be too provocative, in particular because much of your activity is based on graphene oxide. But in my opinion, graphene oxide has some problems. It's too easy to get it, right? But for sensing, well, for chemical sensing, I stopped to use it totally because, I mean, there are too many background interactions that you cannot control, such that I think that will limit anyway the selectivity. So for pressure sensing, that's less interesting. But the MOS2, for example, is much easier to functionalize. You can use this thiolated molecule. You have thousands of thiolated molecules in the Odre catalog, so they have everything you need because they've been developed for gold, you know. So I think the future is probably going towards more and more, let's say, structural complexity, hybrids, but also starting from liquids. Okay, not only the hybrid, the van der Waals approach of physicists that they put physically one flake on the top of each other, but also starting from liquid, they can be control reactions such to create a new hybrid structure. And hybrid structure means to increase the functional complexity of the material.
Okay, thank you very much, Paolo. Any questions? Please.
Paolo, very impressed as always. Always nice to see all the progress in your lab. So it was curious when you mentioned the use of the solvents can also dope your material. So when you do the functionalization, then you have this, like you need to play the role of the molecule and solvent, or
You have to do always a blank experiment to see what was the contribution in terms of doping of the solvent. But if you can deposit from the vapor phase, that's always better. Like the butanediol, we were depositing from the vapor phase, if I remember well. So you just evaporate, or yeah. So with small molecule that you iterate, I mean, without needle going to vacuum, you just you put a closed environment and you iterate a bit your material, and there is some molecules that are enough to create a monolayer on the top of the surface. Because I mean, solvent, even the simplest one I was listing there, when I saw the result, I was depressed because, yeah.
Imagine. And then for the networks that you are
Yeah.
also synthesizing, you are thinking also to put some kind of photographic molecule there that you can.
Yes, yeah, of course. We are on it. But it's not easy. We try with the benzene, didn't work. We had a few problems where we are trying with diarylating. We had a problem with the first batch of diarylating because now we start to synthesize the photochromic molecule. I have a synthetic person in the group. So we wanted to innovate also on the photochrome. It was, let's say, we did too much. So now we have to go back to a more standard diarylating with 2 thiolated unit that has been already reported, and we are on it. Yeah, thanks.
Okay, thank you. Any other question for this?
I have one regarding like the processability of this branch of new material that you're mentioning, like also the point of the solvent doping.
Yeah.
For us common mortals that we are working outside the clean room, for example, like, do you think there's space to play around with this? Also, like, for example, like the defects that you're mentioning, to play in your favor, in this case, using like solvents or these kind of things to try to increase, because like, for example, for the graphene now, there's a lot of people that is trying also to process it in ways that you can handle it in liquids, for example, deposit it, inject printing or other stuff.
Yeah, I mean, yes, I think it's the right approach to try to find a way to bring to your advantage. So, but it depends on the goal of your research, So in fact, they can be used, for example, for healing defects in MOS2. But there you can think about even gases, like, for example, now we have some evidence that you can simply, there was an idea that I had in the past, you take a CVD, let's say, if you have a roll-to-roll production of CVD MOS2, then say, but there are a lot of defects. I mean, if one defect every time by 10 nanometer you have in the Scotch tape, in the CVD is much more, okay? So, I mean, if you are an electronic industry, okay, you want to produce MOS2, then you want to sell it, okay? So my idea was you do a roll-to-roll production of CVD, then you spray some gases that, like, of course, when you put tiles, everything stinks. So that's the problem. Like H2S, that was my goal to spray H2S, and then it was part of the roll-to-roll process. Now it works. The main problem was that I had to convince the lab to use H2S. And so in my lab, you cannot do it. Then I said, maybe in China, they are willing to do it. And then they said no. Then I tried with Poland, they said no. And then at a certain point, I found a guy in Dresden, not Xiliang Feng, because Xiliang said no. But there is Giovanni Cunibert, a theoretician, that is small lab also in experiments. I think the fact that he has a very, let's say, physical culture of computational physics. He didn't realize how much it was stink. So I said, in my lab, you can do it. So we went there to do it, and it works, okay? So so that is an example. But you can do also with methanethiol. You can do with, so it's an example of how you can turn this kind of reactivity to your advantage. I think that's the only way to do it, because you cannot get rid of it.
Any other question? So if not, let's thank again Paolo for this fantastic talk, and thank you very much for coming here, and wish we'll extend the collaboration. So thank you very much.
Thank you very much to all of you.